Hi everyone, what we've got here is our presentation on C4 of the energy subtopic, and that is on solar energy. As always, let's start with the study guide. I am pretty much going to be covering all of these. And yeah, just keeping in mind that it's only those double bonds. Okay. So what we've got here are two images directly from the data book. Now these are all the way up the back. Now there are a couple of things that we need to keep in mind. Conjugation is this idea, and let's look at the alpha carotene as an example. We've got the alternating double and single bonds, double bond, single bond, double bond, single bond. And what that does is it actually changes the light absorption of this molecule. So most organic molecules, as we discussed in the organic topic, absorb light in the UV range. That's why UV light is such a powerful catalyst for organic reactions. But when we look at something like alpha carotene, and as the name suggests, this is in carrots, it is that orangey colour. So what this conjugation allows, so conjugation is the alternating double and single bonds, that decreases the absorption energy and it changes it from being UV sensitive to visible light. Sorry. Another example of a molecule with conjugation is chlorophyll. So if you'll see here, we've got a whole bunch of alternating double and single, double, single, double, single. You've got these double, single conjugation all the way through this molecule, and it's photosynthesis that allows that chemical reaction that you already know about, because I'm pretty sure I've already spoken about it several times. So plants take in carbon dioxide from the atmosphere and water, and they end up making glucose and oxygen. So it's this glucose that we can then go and do further stuff with, which we're going to talk about next. Okay, so biomass, the equations in biomass are using the products of photosynthesis. So this chemical reaction, the amount of solar energy that actually captures is only about 0.06% of the energy from the sun. So if we look at the energy efficiency of this process, it's actually incredibly low. But because there is so much solar energy and because it is so ubiquitous, it does make it a lot easier for us to use this on a regular basis. So biomass, so I can use it directly. So this is the process that makes glucose that goes into plants. So, sorry again. Using that directly, if I have a barbecue and I add wood, so if I've got a wood-fired barbecue, I am directly using the products of photosynthesis as an energy source. There's then biomass decomposition. So one thing that they're starting to look into in a number of places, Australia, we're not doing it, but if, for example, you had a container and you did anaerobic, so no oxygen, decomp. So if I did anaerobic decomposition of carbohydrate containing products, I end up with methane, which, as we discussed in the fossil fuels video, that's actually quite a useful fuel source. We can then, another way we can use biomass as a source for energy is by fermentation. So fermentation is where I take C6H12O6 and I convert that into C2H5OH. So I'm making ethanol. And I also make carbon dioxide. So if excuse me a second. Okay, so how this balances is I end up making 2 of each of those. And once I've got my ethanol, I can either burn that directly as a fuel, or I can combine with petrol to make something called gasohol. So it's gas as in the American word for petrol, and then the ending for alcohol. So the benefits of doing that combined gasohol is that even if I can replace 10% of the petrol in an average car tank with ethanol, it decreases the amount of crude oil that I'm refining to make petrol. It makes some of it renewable. It makes a portion of that renewable. The big downside is that this gasohol has a lower boiling point than standard petrol, which means that it actually evaporates, which means you get some loss as you actually just do transport and things like that. Okay, let's continue on. So vegetable oils are produced completely naturally by plants. So you might have heard of palm oil, which is an important crop in other parts of the world. It's used in a lot of stuff. Now, if you were listening when I was teaching the biochem people about oils, this is where that's going to come in handy. So oils have the same basic structure. So there's a molecule called glycerol. Sorry, let me draw it a bit more neatly. So I've got a 3-carbon backbone with OH groups off it. So this is this is a molecule called glycerol. And then what happens is when it's an oil, it forms an ester with 3 fatty acid molecules. I'm sorry, I probably should have picked colours that contrast a little bit more. But these are produced naturally by the plants. We don't have to trick the plants to make this. So these vegetable oils, think about something like olive oil or coconut oil or whatever it is you've got at home. Those tend to be very what's called viscous. That does not look like I've spelt it correctly, but it feels like I have. So the definition of viscous is that it pours slowly. So think about when you're pouring, I'm going to go with olive oil because that's what I've got in my pantry. When you're pouring olive oil into a pan, it gloops. It doesn't pour like water. So something like olive oil has a higher viscosity than something like water. So if something is viscous, it pours slowly. And because this pours slowly, even when it is warmer, it's not really suitable for use in car engines as it currently is. So these vegetable oils are produced by the plant. It is a renewable process. But as they are in this form, and I'm going to switch to laser. So this form here, they're too viscous to be used as a substitute for something like diesel. So we're talking about diesel substitutes. But in this form here with the glycerol attached, it's far too viscous to be used as a diesel substitute. I need to do a second process. And that's where esterification comes in. So we've got, and I should have copied and pasted this from the previous slide. Then you've got your, and I'm just going to call them R1, R2, R3. These R1, R2, R3 can be pretty much any carbon chain. There's no particular R group that has to be. There are examples of the different fatty acids in the data book up the end. I can't remember exactly what section. So basically what I can do, esterification. So like transport means to move between ports. Translation is to change between languages. Esterification is to change the ester. Oh, be good if I could spell. So this glycerol molecule, I mean, spoilers, but this is going to end up reforming the glycerol molecule. And I'm going to end up with fatty acid esters. So I'm going to end up with, COR1, COR2, and COR3. So I need something that is going to replace, and I'm going to go to my laser, I need something that is going to replace this ester bond with a different one. So you can see that my glycerol is effectively an alcohol molecule. It's actually a polyol. Is that a thing? I don't know. It's 3 alcohol groups on a molecule. So I just need to make sure that when I'm adding something, that it has that hydroxyl group. So we would normally add 3 methanols, and we tend to do it in an acid catalyst. What that ends up giving me is CH3O, CH3O, CH3O. So I end up with methyl esters. Now, the reason we do this, because these molecules are smaller, so these, again, let me laser pointer, these methyl esters are approximately 1/3 the molar mass of the original fat. It roughly works out that way. So these methyl esters are approximately 1/3 the size, which means that my LDF is going to be much smaller. Remember, LDF basically comes down to the smaller the molecule, the lower the intermolecular force. So these methyl esters have much lower viscosity. And these can be used as a direct substitute for diesel. So I remember even years ago there were stories about people going to fish and chip shops and taking their old oil. So most cooking places, you can tell I haven't been out of the house in a while. Most restaurants have like they pay services to come and collect their oil. There are, at the time we thought crazy survivalists, now they just seem ahead of the curve. People who used to go and drain the oil and then react it with either methanol or ethanol to make either methyl or ethyl esters and then use those as a diesel substitute. So the energy, like the energy per mole of, so the energy per gram is actually pretty similar between my fat and my methyl ester. The advantage of a methyl ester is because it's got the lower viscosity, it can be used to substitute for diesel. Please note, this is still a biologically derived reactant, which means that this is renewable. Methanol can also be made renewably, and we saw in the previous page or before that ethanol can certainly be made renewably. Okay. So just like everything else, biomass has its advantages and disadvantages. The advantage is that it's renewable. We can be continually replenishing our stocks of biofuels. They're also, it doesn't exactly work out, but it is largely carbon neutral. So ignoring the energy costs to transport biofuels from place to place, generally speaking, all of the carbon atoms that are burned came from the atmosphere to begin with. It's comparatively easy to transition. The technology is already in place. So, for example, we already have diesel engines that can use biodiesels. We have petrol engines that can use gasohol. But this is balanced out by some of its disadvantages. The disadvantage is that it doesn't actually so what I mean by doesn't stimulate change, if we transition from using diesel to using biodiesel, we're still reliant on something that is effectively still just a carbon fuel. We're not actually incentivizing any sort of change to move us away from that carbon-based economy. Another disadvantage is that it uses a lot of like farmlands. So it takes up a lot of what could be like food crops, which in a world where food resources aren't distributed evenly, it isn't necessarily the most equitable way of doing it. There's also lots of fertilisers. because we have to use fertilizers to grow these crops. The fertilizers themselves aren't necessarily carbon neutral, and also nitrogen and phosphorus, which are the two main ingredients in most fertilizers, they can cause algal blooms and other pollution effects. So just like every other technology we've looked at, biofuels might be a part of an energy solution, but they are not an answer in and of themselves. Okay. So in this session, we talked about conjugated electronic structures. We did this equation, which you should be able to recite in your sleep at this point. We talked about ethanol fermentation. We talked about viscosity and how that relates to vegetable oils and diesel. We talked about transesterification. And we talked about what the transesterification was. I only talked about it in the presence of a strong acid, but it can also be done in a base. And we talked about transesterification producing oils with lower viscosity. We identified the feature, so that alternating double and single bond. We talked about reduced viscosity and why. We evaluated the advantages and disadvantages, and we deduced an equation for a transesterification reaction. Okay, thank you so much. Have a fantastic rest of your day, and I'll see you next time. Bye.